Hello students, I hope you are using this lockdown period effectively for preparation of the examinations. Now let's start with the next chapter, that is called as application of spectroscopy. The application of spectroscopy is related to the first module, that was principles of spectroscopy, where in this principle of spectroscopy you have studied what you understand by a wave, what you understand by electromagnetic spectra, and what are the different types of waves spectra, which we starts from the radio waves and the other frequencies. Then we have seen the spectroscopy and the classification of spectroscopy. In a broader aspects, we have seen that spectroscopy can be classified into absorption and emission spectroscopy. So in this chapter, we are going to study one of the application of spectroscopy in the area which is called as atomic absorption spectroscopy. Now, atomic absorption spectroscopy, which is called as AES, it is a method of chemical analysis that uses the intensity of light emitted from either a. Now, in order to use the emission spectroscopy, this can be carried out by using different sources. So, if we use flame, then it is called as flame emission spectroscopy. If we use plasma, it is called as plasma emission spectroscopy. If we use arc, then it is called as arc emission spectroscopy, and it can be carried out by spark, which is called as spark emission spectroscopy. Right. So with all these sources, what we can see over here, we can have the emission spectroscopy. Now in this applications, particularly what we are going to study in detail, which is called as flame emission spectroscopy. So at a particular wavelength, this is carried out to determine the quantity of an element in a sample. The wavelength of the atomic spectral lines gives, what is important to know, that it tells you about the identity of the element, that is, it tells you which element is present in the sample, which metal or metalloids element is present in the sample. Also, what we come to know is the intensity of the emitted light, and this intensity of the emitted light is proportional to the number of atoms of the element. So with this you can understand, by the emission spectroscopy we can come to know the nature of the element present, and also we can know what is the concentration of the element which is present in the sample. So flame emission spectroscopy. Flame emission spectroscopy is particularly based on, let's see what is the principle on which the FES is based. The liquid sample containing the metal salt solution. One of the important thing is that it is generally used for identification of metal and metalloids. So it should be in the solid form, and it is mixed with the liquid sample to form a solution. So a liquid sample containing the metal salt solution is introduced into a flame. As I have told before that we are going to study what is called as a flame emission spectroscopy. So what we are going to use, the source for excitation is nothing but it is a flame. Then the solvent is vaporized, okay, with the help of this flame. First the step takes place, it is the vaporization of the solvent, leaving particles of the solid salt. So first step is the vaporization of the solvent takes place, then the salt is vaporized into gaseous state. Next stage is that the metal salt which is present, then it gets vaporized to the gaseous state. When it gets converted to the gaseous state, the next state is the gaseous molecule dissociate to give neutral atoms. So what do we get is the neutral atoms. Further, when it gets converted to atoms, the unstable excited atoms emits photons while returning to lower energy state. So when this excited atoms comes to the ground state or the lower state, it emits a particular amount of light, that is, it emits photons of a particular wavelength. The measurement of emitted photons forms the basis of what we call as the flame photometry using photomultiplier tube detectors. So this is what the principle of flame emission spectroscopy depends on. As you can see in this diagram, we have the electron. Okay, this is the electron which is at the ground state. Then it gets thermally active by using flame photometer. This electron gets excited towards the next excited state that we can consider as E1. Okay, so when this electron gets excited, that is called as the absorption spectroscopy. Because of the heat, the electron gets absorbs the heat and gets uplifted to the next excited state. Now the electron cannot remain for a longer time into the excited state, so it comes downwards back to the ground state by emitting photons of a particular wavelength. This is what the flame emission spectroscopy is based on the principle. I hope it is clear to you. Now, depending upon the flame, what we can see that whatever the element is present, and that element will give specific wavelength. At a specific wavelength only we will get at the particular element we gives a particular emitted wavelength, and it will give a different colors which are obtained in the flame. The flame color changes accordingly. So as you can see in this table is nothing but emitted wavelength and flame colors of the various alkali and alkali earth metals. If you can see the potassium it will emit the photons at a wavelength of 766 nanometers, and the color of the flame is violet. So if we see the color of the flame turns to violet, it means that it is the element which is present in the solution is potassium. Same goes for lithium. The lithium emits the photons at a wavelength of 670 nanometers, and the flame color changes to red color. If calcium is present, the calcium will emit the photons with a wavelength of 622 nanometers, and the flame color is orange. If sodium is there, then this sodium will emit the photons at a wavelength of 589 nanometers, and the color of the flame is yellow. Same if barium is present, the barium will emit the photons at a wavelength of 554 nanometers, and it will give the color that is, it is a lime green color. Okay, so with this we can come to know what is the color of the flame, and depending on the color of the flame we can know which element is present. So if it is either orange, so it comes to calcium is present in the sample. If it is yellow, then we can say sodium, and so on. Okay, now let's see how what are the various steps involved when this process of flame emission takes place. Emission of the element in the using flame photometry takes place, which is labeled as events occurring in the flame. Now let's see what are the events. The first step is called as desolvation. Now what do you understand by desolvation? Desolvation is nothing but the metal particles in the flame are dehydrated by the flame, and hence the solvent is evaporated, right? So this process, in short, it is nothing but evaporation of the solvent. We have prepared a mixture which consists of the specific metal which has to be identified, and it is dissolved in a particular solvent. So when it is applied, when this mixture goes into the flame, the first process what will take place is the evaporation of the solvent. That is called as desolvation. D is removal of the solvent. Okay. The second one is called as vaporization. Now please don't get confused in the solvent which is already evaporated. Now what is this vaporization? But vaporization is where now what the solvent has been evaporated. Now what is remaining? The metal particles. The metal particles in the sample are dehydrated. This also leads to the evaporation of the solvent. So the metal which is present in the solvent, that solvent is first of all removed out by the vaporization which is present. Okay, the next one is called as the atomization. Now with the word you understand, atomization is nothing but converting into atoms. So reduction of metal ions in the solvent to metal atoms by the flame heat is called as atomization. So atomization is the formation of metal ions into atoms. Atomic state is called as atomization. Then when it gets converted to atoms, now which is the next step is called as the excitation. So what happens in the excitation? The electrostatic force of attraction between the electrons and the nucleus of the atom helps them to absorb a particular amount of energy. The atoms then jump to the excited energy state. So in the excitation, the atom then moves out to the next energy level as it gets excited. When it goes up to the excited state, now then what is the last step, which is called as emission process. Now in this emission process, what happens? Since the higher energy state is unstable, okay, so this energy state is unstable. Now suppose there is a good news, you have got good marks and you are happy, but how long you are going to be stay happy for that? Hardly for 1 or 2 days, again you will come to your normal mode. So similarly, the electron which is excited at a higher energy state, it is unstable and it should come back to the ground state. So during this procedure, what happens? The atoms, when it comes jump back to the stable low energy state, it emits energy in the form of radiation of characteristic wavelength. So this characteristic wavelength, why it is called? Because it will emit the wavelength whatever the metal ions which are present in the flame, and this is measured by a photo detector. Okay, this is how, what are the various steps involved in the flame emission. That is, the first one is called as a dissolution, second one is vaporization, third one is atomization, next one is called excitation, and the last one is the emission process. So this is the diagram which tells you the energy level diagram of atomic sodium. Okay, atomic sodium, we know atomic number is 11. So we have one electron in the 3s orbital, which is the last electron, unpaired electron is present. What is the configuration? 1s2, 2s2, 2p6, 3s1. So this 3s electron can jump from 3s to 3p, or it can go then from 3p to, this is 4s, 3s, this is 4s, and the upper one is 5s. I could not write it properly with this. Okay, 4s and 5s. So the electron can jump from 3p to 4s, or from 3p to 5s, where the wavelength is around 616 nanometers, or it can go from 3p to 3d, okay, or 3p to 4p, and this is the wavelength which is exerted. This is how the energy level diagram of atomic sodium takes place, and it obeys the selection rule that electron can't jump from delta S should not be equal to 0, that is electron can't jump from 4s to 3s or 5s to 3s. Okay. So the intensity of the light emitted could be described by Lomakian equation, which tells you that I is equal to K into C upon N, C raised to N, sorry. So where I stands for the intensity of emitted light, C stands for the concentration of the element, K stands for the proportionality constant. When N is nearly equal to 1 at the linear part of the calibration curve, then we get the formula that I is equal to K into C. So we can conclude with this equation is that the intensity of the emitted light is directly related to the concentration of the sample, as K is a constant. As we can see, K is called as a proportional constant. So what is our equation? I is equal to C. So intensity of the emitted light is directly related to the concentration of the sample. Okay, so this was what about we have studied in this video. We'll proceed further in the next video. Thank you for watching.